give me the opportunity to present our recent results with Nicolas Pavlov, my supervisor. And before starting the presentation, I would like to add some words about Renaud Parentani. I didn't know him very well, but I had the opportunity to discuss with his close collaborators, and in particular, Scott Robertson and Florent Michel. And I benefit from the deep understanding of the field triggered by Renaud in his team. So now I will come back to the presentation, and I will try to be brief at the beginning. Here we consider an acoustic black hole in a Bose-Einstein condensate. So we take a quasi one-dimensional BEC, and this condensate is described through a one-dimensional field operator, which is a solution of the Gross-Pitayevsky equation. And in this equation, you have the nonlinear term here in blue, which accounts for repulsive interaction between bosons. And you also have this term in red, which is an external potential. And by means of this external potential, you can create a dissymmetry in the density profile of the condensate. So here you can see an image which is extracted from a result from Jeff Schenauer, published 4 years ago. And as you can see, this is obtained by absorption of light. This region is a region of high density, while this one is a region of low density. And here we are in the co-moving frame where the potential is moving from right to left. And here you can see that this is a step-like function. So to understand it a bit naively, imagine now that we are in the laboratory frame where the step-like function is fixed at x equals 0. Then the condensate is moving from left to right, and here these blue dots represent the particles in the condensate. And when they are actually falling down the step, they are going to accelerate. And because the flow is stationary at the vicinity of the acoustic horizon, if the flow accelerates, then you can see that the density is going to decrease. And by means of that, you can create a transonic flow, as you can see in this drawing here, with a subsonic and a supersonic part. And in the middle, the horizon splits the whole system in 2 parts. So then in the condensate, there are some quantum vacuum fluctuations, which gives rise to the emergence of elementary excitations. Here's the example of such a pair created from the horizon. And they behave as sound waves in the low energy limit. And to give you an idea of all the elementary excitations that we can have in our system, you can calculate the range of the dispersion relation within a Bogoliubov approach. And for a fixed energy, which is here represented by this pink line, you can have different channel of emission and the propagation channel. So for example, in the subsonic part, you have this H channel, which will correspond to the Hawking channel. And in the supersonic part, you have the P channel, which is a partner, and also in our case, the C channel, which is a companion, and this is also called the spectator. So to sum up all the elementary excitations that we have in channels. These are excitations which travel towards the horizon. And then, as you can see, there is a process of scattering, and you get some out channels. And we are particularly interested in the Hawking channel here, which propagates away from the horizon in the subsonic part, and the partner, which propagates inside the acoustic horizon. And this analog Hawking pair is highly correlated, as we are going to see a bit later, and also strongly entangled. So then we can quantize the theory by defining what we call the ingoing and the outgoing quantum modes. And these modes are actually a combination of different in and out channels. And to give you an example of that, here you have an ingoing mode B of H, and that corresponds to an elementary excitations going from the subsonic region, which is going to scatter onto different out channels. And all this process of scattering defines an ingoing quantum mode. And you can have also outgoing mode. And what is important here is that you can choose either the set of ingoing quantum modes or the set of outgoing quantum modes to construct the Fock basis of the system. Another point to underline is that the outgoing modes and the ingoing modes are linked through the so-called scattering matrix. And here, the coefficient of the scattering matrix are nothing but the reflection and the transmission coefficients of each scattering process. And apart from this quantum mode, there are also what we call the zero mode. So I don't have much time to discuss this in detail, but if you have a question at the end, of course, I will answer to it. But what is important here is that the quantum operator which describes the quantum fluctuations can be written as a combination of the ingoing quantum modes plus these zero mode operators, which are related to the phase and to the number of particles in the condensate. And what we realized with Nicolas recently is that to get a correct normalization of the quantum operator, you need to add the zero modes, and then you have this correct normalization. And now that we got this, a well-founded theory, the question is, where is the Hawking radiation? And the direct measurement might be a bit difficult because of the thermal noise in the system. And this is why there was this idea to look at density correlations. And that was a groundbreaking contribution in 2008 by collaborators in Trento and in Bologna, among them Jacopo Causotto. And here you can look at density correlation because all the emitted quanta which emerge from quantum fluctuations are correlated. So if you are able to calculate this correlation function, the G2 function, which is given here, then you can detect indirectly the presence of such quanta in the system. So again, I will be very brief here, but imagine that a Hawking pair is emitted at the horizon initially, and you want to follow the trajectory of this pair at equal propagation time. Then you can do it in a 2D graph. So here I put a green dot in the middle because initially the pair is exactly at the horizon. And then you can follow this trajectory because you see the pair is going to propagate, and this line here exactly corresponds to the trajectory of this pair. And by symmetry of the problem, you also expect another line here. And because emitted quanta are correlated, this is where you expect a high correlation signal. And indeed, when you calculate the G2 function, this is the kind of correlation patterns that you can obtain in real space. So you see a lot of correlation lines because they are not only the Hawking and the partner, but there are a lot of elementary excitations which are created from the horizon. And importantly, there is this blue dashed line that you can see here. And this line here exactly corresponds to the trajectory of the Hawking pair. And indeed, this is where we, as you can see, this is where we have a very high anti-correlated signal. So just to emphasize again the importance of the zero modes, you can make a cut, and here an horizontal cut, which to plot the density correlations along this cut. This is what is done here. And you see that the correlation signal, when you don't take into account the zero modes, presents some spurious oscillations. And they are totally removed when you take into account the zero modes. This is a red curve. And then you have a very smooth transition from the subsonic to the supersonic region. And that was very important for us because we wanted to get a correct description of the G2 function at the vicinity of the acoustic horizon to be able to compare our theoretical results with a recent experimental one, which was performed by Jeff Genower and collaborators and published last year. So here what you see are the experimental correlations. So you have the diagonal here, which accounts for the quantum depletion of the condensate. And you also have these two lines, two correlation lines here and here. And if we do the same, if we calculate theoretically the correlation pattern, this is what we obtain in the vicinity of the acoustic horizon. And as you can see, the blue dashed line here corresponds to the Hawking correlation signal. And in the experimental paper, James Stanover and his collaborators made different perpendicular cuts to the correlation line, where they were able to extract the correlation signal. And this is the experimental data that they got. And this, just to mention that this result was obtained, was average over many cuts along the correlation line. So you see that when you cross the correlation line, you have the minimum of correlation just here. So we decided to follow the same procedure and to also make several perpendicular cuts along the correlation line. And this is what we obtained theoretically after averaging over many cuts. So this is a red curve. And as you can see, we can reproduce quite well the width and the depth of the experimental data. And now one can study in more detail the characteristics of the analog Hawking radiation. And in particular, we looked at the Hawking spectrum in BEC, which corresponds to the correlations in K-space. And here you can see that, just a question of definition, this KH and KP are the wave number of the Hawking and the partner quanta, computed at the same energy, omega. And if you compute this quantity, you are going to find that it can be expressed in terms of the scattering matrix coefficient. And if you make the same calculation, but in the context of general relativity, you will realize that you are going to find this expression where you see this scattering matrix coefficient for the BEC exactly corresponds to the so-called beta coefficient found by Hawking. But the main difference here is that the beta square, Hawking found that beta square was fully thermal distribution, which is not exactly the case for our scattering matrix coefficient, as we are going to see. So here, this is the result of a normalized by the static structure factor of the Hawking spectrum as a function of the energy in reduced units. So the red curve corresponds to this quantity here in the case of BEC, and the gray curve is obtained from this expression here. So it will correspond to the Hawking radiation emitted by a gravitational black hole at the same Hawking temperature, which is written here. So, and we also added the experimental data, which were given by Jeff Stanover and extracted from his paper of 2019. So as you can see, what might be surprising is that we had a very nice agreement with the experimental data in terms of the correlations in real space, but this is not exactly the case for the correlations in K-space. And this is even more surprising that to compute these experimental data, Jeff Stanover used one of its findings in 2015. So he was able to prove that the correlation in K-space were directly obtained from the Fourier transform of the G2, so of the correlations in real space. And for example, here you have again this correlation pattern, and you can choose the green rectangle, for example, over which you compute your Fourier transform. And of course, you have to choose the KH and KP such that they are at the same energy, and this should, and you should get at the end the Hawking spectrum. And there was another result published the same year by Denova, Sols, and Zapata, and they studied the correlations, and they found that one need to impose a ratio of the length of the rectangle in terms of the group velocity. So to physically, you can explain, so you can have a physical explanation of this prescription, because you see here this drawing, the time needed for the Hawking quantum to reach the center of the upstream length that you choose to compute your Fourier transform should be the same as the time needed for the partner to also reach the center of the downstream length that you choose for the windowing. So, but in a dispersive theory where the dispersion relation is not fully linear, you have actually to change, to adapt the windowing, so the dimension LU and LD, for each value of the energy. And with Nicolas, we wanted to study the effect of this prescription and so to the effect of this prescription. And we choose a windowing which is adapted to a dispersionless theory, so where the dispersion relation is fully linear. And if you do that in a dispersive theory, then you realize that there is a damping of the signal. And indeed, the Fourier transform of the G2, by doing the Fourier transform of the G2, you indeed get the Hawking spectrum, but there is a damping factor whose explicit expression is given here. And to sum up what we have, so again, the red curve is obtained for a BEC and by choosing an energy-dependent windowing. And then if we choose this windowing which is adapted to the dispersionless limit, so in our case for the low energy regime, then you see that there is a damping of the signal, and the blue curve is very close to a Planck spectrum. So this is what we discuss in our paper. But beside that point, we also mentioned that there are some characteristics of the analog Hawking radiation which point to thermal spectrum. And here you can see that thermal is in quotes because thermal is in quotes because we have to define very carefully what do we mean by thermality. And to look at that, one can look at the Hawking population. And here, if you look at the Hawking population, it means that you are only interested in the Hawking channel, which goes away from the horizon. So it means that you completely forget about what's going on beyond the acoustic horizon. And the quantum state of the black hole is pure, but because you are only looking at the Hawking channel, then the system is described by a mixed state. And so when you calculate the Hawking population, you have to take a reduced density matrix. And it turns out that this reduced density matrix is the one of a two-Moss squeeze state. And here, this is the explicit expression of the reduced density matrix, which can be expressed in terms of a squeezing parameter. And this squeezing parameter can be also expressed in terms of the scattering matrix coefficient. So with that, what you can do is then to calculate the Hawking population. And indeed, you are going to get a thermal spectrum. But the main difference here is that the effective temperature which appears in this distribution depends on the energy. So this is quite different from the gravitational case, because as you can see on this graph, we plot in the effective temperature as a function of the energy, and only in the low energy limit, the blue curve is almost constant, which means that we get a Planckian spectrum, but then the effective temperature is no longer constant, and so the spectrum deviates from a fully Planckian spectrum. Okay, so I think I will.
1.5 minutes left.
Sorry?
1.5 minutes left.
Okay, so that's perfect, thank you. So to conclude, you can see that analog gravity is really an exciting platform to study fundamental questions related to gravitational black hole. But this is also for us a very great platform to connect it to nonlinear quantum optics and to study the coupling between nonlinear matter waves and quantum effects. And there are been exciting experimental results obtained by the Tenon group very recently, which provide indisputable evidences of the occurrence of the sonic horizon and the associated acoustic Hawking radiation. And as I said during this talk, there are many characteristics of acoustic Hawking radiation which point to a thermal spectrum, although some aspects are a matter of debate. And natural development in the future will be to focus on the dynamical features of the acoustic black hole at the vicinity, in the close vicinity of the acoustic horizon, because we have now everything to describe correctly, for example, the correlations, and that will be a natural development, but in the future. And with that, I thank you for your attention.
Thank you very much. Thank you. So it's time. It's first time for the questions.
I have a question. Do I just ask it, or do I send a message that I raise my hand and all that kind
Jeff, that's you, right? Hi, Jeff.
Yes.
Yes, please go ahead.
Okay. So I have two main comments. The first is the experiment wasn't actually analyzed in a rectangle. Like the rectangle you showed that you analyzed your simulation was not the same kind of rectangle that we used to analyze the experiment. We used a rotated rectangle. We just used but anyway, that's a technical detail. The kind of rectangle you showed would let a lot of noise in if we analyze the data in that way. But my main comment is your model seems very different from the experiment in that it has so much dispersion. If we can we see again like the profile that you showed, the
yeah.
Yes. So for example, this one, for example. So you have the dispersion peak on the left side of and it's much bigger on the red, in the red curve.
Yeah.
There's a big peak on the left at -2 and 0.3. No, in the red curve, down below, the one-dimensional curve, there's a big peak on the left.
Yeah, exactly. Yeah.
Can you point at that so other people can see what I'm discussing? Yeah, this curve, yes. The peak in the theory is much bigger than the peak in the experiment, and that's a measure of dispersion. And dispersion is where all your deviation from thermality comes from. Furthermore, you can see in the plots above, the two-dimensional plots, you have these fringes. Really, the peak we were discussing below is one of the fringes in the fringe pattern, and there's no sign of a fringe pattern in the experimental data, which is another sign that there's not so much dispersion in the experimental data. So the deviation from thermality that you see, I don't see how you could compare it directly to the experiment.
Okay, maybe I can answer.
Yes.
Yeah, so yeah, it might be possible, but there is more dispersion in the theoretical results than in the experimental one. But we try actually to remove dispersion in our theory, and then if we do that, we don't have such a nice agreement with the experimental data, and we lose the asymmetry of the profile. So this is why we were not sure of that. So it might be possible, but we just propose a possible answer to the damping of the spectrum. And this is, I mean, from a theoretical point of view, it's clear that by doing this Fourier transform, we cannot reproduce well the Hawking spectrum if it's not appropriate to our theoretical description if we don't choose an energy-dependent window. But that's the thing that we wanted to say today. But then if we cannot prove that there are the difference between in terms of dispersion between the theory and the experiment. But just again, if we remove a bit of dispersion, then we don't get such a nice agreement.
I understand that your theoretical model doesn't work without dispersion, but that doesn't mean that the theoretical model somehow matches the experiment. Maybe the experiment needs some other theoretical description, which is not similar to yours or something, because there's this big difference in dispersion between the experiment and the model, and the dispersion is what gives you your deviation from thermality. So just, so comparing with the experiment seems a little problematic to me.
Yeah, but
I agree. Even your coworker Nikolai, Nicolas said he finds it puzzling that there's this difference in dispersion. So one would need to find a theoretical description which would match the experiment and including the dispersion characteristics. Then one could assess thermality within this unknown theoretical model.
Okay, if I can just add something, maybe this graph very quickly. So we try to add this to give a dispersionless model or something which is between true dispersionless model and the dispersive model. But then you see there is the profile become very symmetric, as you can see, and the width is not reproduced very well. And then yes, it's true that here the agreement. So maybe for this dispersionless model is not very is not very good, but we try other dispersionless model and we can fit this part. That is true. But then we completely lose the width of the experimental data.
Right, and then I see on the right that it's perfectly thermal, this dispersionless model.
Yeah, of course. When you choose a dispersionless model, this is exactly. Yeah.
Yes, so one needs a model that really matches the experiment. Then one can check if it's thermal or not.
Yeah, but you see what is surprising is that, yes, it's true that this is, sorry, I cannot remove the chat. Okay. So yes.
I have to,
yeah,
I'm really sorry. Perhaps because Jeff is giving a talk later on, perhaps, do you want to continue? I don't want to cut you off. I also think maybe you also want to discuss this privately or continue after Jeff's talk. And then, because I think it was quite a dense program, everyone is probably longing for a coffee. And it seems to me that this is a longer discussion. So let's just interrupt it for now. And thank Mathieu again for his talk, everyone.
Thank you.